Hello, everyone, and welcome to our next virtual live at Frost Science. We're so excited to have you join us here today. And we're very excited to have our special speaker, who's a professor at the University of Florida, Dr. Sara Ballard. So with this series, for those of you that have been watching, we, encourage you to ask questions throughout the entire presentation. Welcome to our next virtual live at Frost Science. We're so excited to have you join us here today. We're very excited to have our special speaker, who's a professor at the Sorry about that. Not fun to listen to yourself talk. But we're very excited. And for those of you that are joining us for the first time, what we do is we go ahead and encourage you to ask questions throughout as they come up in the presentation, and we want to hear from you. So please use the comment box to ask as many questions as you want, and we are very excited to introduce our speaker. So Dr. Sara Ballard is originally from the San Francisco Bay Area. She earned her undergraduate degree in astrophysics at UC Berkeley in 2007 before attending Harvard University for her Ph.D. She discovered a love of exoplanet research there and earned her doctorate in 2012. She then went on to the University of Washington for a NASA Carl Sagan postdoctoral fellowship. And after that was a Torres Fellow for Exoplanetary Science at MIT from 2015 to 2019. Most recently, she joined the University of Florida to be an assistant professor beginning this last fall of 2019. What an accomplished female scientist, and I'm so excited to have you join us. Dr. Sara Ballard, welcome. Don't worry, there you go. Welcome, welcome. How are you today?
Very well, thank you. Can you see my screen, Angela?
We can.
Great, all right. Thank you so much for that beautiful introduction. I really appreciate that. And for all of you who are listening and watching online, I really appreciate your time and the opportunity to tell you a little bit about all of the exciting science that's happening right now in the field of exoplanets. There's a reason why I titled my talk Directions to the Nearest Alien Earth-like Planet, because I like to try to conceive of the study of exoplanets now in terms of human scales. So not only human length scales, but also human time scales. What does it mean in terms of the last 10 years, what we've discovered as a species about exoplanets, and also what does it mean going forward for understanding these worlds and saying something about them as a whole. So trying to move the field from one individual discovery of a planet around another star to an understanding of how common planets are in our Milky Way galaxy. Any talk about exoplanets, which are planets around stars other than the sun, should start with our own home solar system. So I'm going to show you a video now, which was taken in 2012 of our own home sun. This video was taken from NASA's Solar Dynamics Observatory of the transit of Venus. So you can actually see right now Venus passing in front of our own home star. And this video is really sped up. So Venus takes about 13 hours to sweep across the face of our star. But you can see that Venus going in front of our sun is actually not the only dynamic part of this movie. You can see too the boiling surface of our home star, in addition to the fact that you can see sort of a hint that our star is rotating. And yet, even if all of this dynamic movie was collapsed down to a single pixel and you were removed to be infinitely far away, you could infer the presence of Venus. Okay, so if all of this was collapsed to a single pixel, you could still know that Venus orbited this star, because when it crossed between you and the star, some of the star's light would be blocked. And you could do that even if you didn't have a movie, you only had one single pixel. Let me show you what that would look like. So what we're actually able to measure with transits, so-called transits, which is when a planet passes in front of the star from our point of view, is that we measure the graph at the bottom, which is showing the brightness of the star as a function of, as a function of time. And so we can't see that picture on top through our telescopes yet. What we see is the thing on the bottom. You take a snapshot of the star every few minutes, and then you observe how the star gets some tiny fraction dimmer. And you infer that that must be because there's a planet there. From the depth of that disappearing light, you know how big the planet must have been to block that much light. Pardon. So this is the sum total of the knowledge we had about planets that do this in 2008. Okay, so this is only 12 years ago. This is a family portrait of the planets that had been discovered this way. This wasn't all of the known exoplanets at that time, but the ones who had been discovered using the transit method. So the actual measurements that scientists took are shown for each of these planets in the bottom part of this panel. That's the black part of the curve, where you can see how the star's light seems to disappear for a little while before returning to its regular level when the planet crosses the face and is done with its transit. So the orange-pink blobs are showing to scale the sizes of these host stars, and the black dots in front of them are showing to scale the sizes of these planets. Okay, so at the time, in 2008, this is about half of the family portrait that we knew of. This is 23 of the 52 known transiting planets at that time. So most of these stars are, give or take, roughly the size of the sun. And the planets passing in front of them, that size of dot corresponds to roughly the size of Jupiter. So basically everything that we had detected with the transit method as of 2008 was a Jupiter-sized planet. They tended to be very close into their star, orbiting a sun-like star, except for, now I want you to look at the bottom right-hand corner, the planet that's called GJ 436. This star seems a little unusual. It's smaller than the others, and you can see that this planet is smaller than the other ones we knew at that time. At this point, GJ 436 was the only known transiting hot Neptune. Neptune is 4 times the radius of the Earth. Jupiter is 10 times the radius of the Earth. So at that point, a Neptune-sized planet, GJ 436, 4 times the radius of the Earth, was the smallest thing we had seen transit. Okay, so this was state-of-the-art only about 10 years ago. All of that changed. And it changed because of a singular NASA mission called Kepler. It's pretty easy to describe how Kepler worked. It's basically a single silicon eye. It affixed its gaze to a part of the sky, which is overhead in Miami around midnight in April or May. And the size of the part of the sky that it looked at, that it stared at, is about the size of your outstretched hand held at the end of your arm. So if you held it over your head, went outside at midnight in April or May, and you look straight up, that's about the part of the sky that Kepler looked at. And it did not look away, hardly at all, for a period of 4 years. So it was launched in 2009. And it was looking at this part of the sky, stars that reside in this part of the sky. So this is now showing the Kepler footprint, the actual eye and what it saw. It was looking for, in stars in this part of the sky, that telltale dimming signal that tells us whether or not planets reside in this part of the sky, because they cross in front of their host stars and then cause that star to look a little bit dim. So it was looking at a lot of stars at once, all in the same part of the sky. This is actually showing you the sum total of the knowledge that we had at that time about the existence of planets in this part of the sky prior to the launch of Kepler. And what you can see that toward the upper right, there's a yellow rectangle that says trace 2. Okay, so that was one of the planets in the previous slide, in the previous family portrait, known prior to the launch of Kepler, a hot Jupiter. As of 4 years later, these were all of the planets that Kepler had found by the end of its nominal mission. And there's 2 things that I want to impart to you about this plot. So Dennis Overby of the New York Times, when he was describing the Kepler mission, referred to this as the Skittles diagram. And these Skittles have meaning. So not only is this showing you, first of all, how overwhelmingly common planets are in this part of the sky, and that must mean that they're common in other parts of the sky too. It's also that they have a real interesting diversity of size. So the flavor of these Skittles is telling you the size of the planet that orbits a star that's in this part of the sky. And where blue is the size of the Earth, remember I said Neptune is about 4 times the size of the Earth. Those are about orange Skittles. Jupiter's 10 times the size of the Earth. Those are red Skittles. So the first thing to notice, remember when I showed you the family portrait before, they were all Jupiters. So those would have been all red Skittles, nearly all, with the exception of one orange skittle that we had prior to the launch of Kepler. Now it seems like actually they are intrinsically rare. The most common type of planet seems to be sort of a super Earth, what we would call in size. These are things which are intermediate in size between the Earth, 1 times the radius of the Earth, and Neptune, 4 times the radius of the Earth. In our solar system, we don't have any planets like that. We don't have anything between the largest of the Earth-sized planets, which is Earth-like planets, which is Earth and Neptune. So this is only one way in which exoplanets are a unique laboratory for us to understand planets generally and to understand ourselves. And I see that there's a question. Wait, you're muted.
We're starting to get questions in. This is so fascinating. We have a question from Lily. She wants to know, are exoplanets only found within the Milky Way?
So far, they have only been detected in the Milky Way, but it's because we don't yet have the precision to find them in other galaxies. So that's the only reason. It's not that they're not there. We can't yet see them. And
so I actually had a question on that too, because I see the smallest size that we have here in this beautiful Skittles diagram that makes me hungry, some candy, is Earth size. So is the technology just not able to view planets that are smaller, like Mercury size or some of these other smaller planets yet?
Yeah. One thing that I wanted to communicate about this picture between this one and the previous one, it's not that there were only Jupiters to be found. It's just that prior to the launch of Kepler, we were only able to grab the lowest of the low-hanging fruit on the tree. So the Earth-like planets and smaller planets like the Venuses and the Marses and the Mercuries out there, you can imagine them at the very top of the tree, like really small planets, very tasty planets. But you need increasing technical precision to be able to see smaller and smaller planets. So this was a huge surprise to us, a very pleasant surprise, if I can put you in the mindset of a scientist looking at this diagram, especially in 2013 when Kepler was observing the sky, which is, oh my gosh, smaller planets are common. It's not before what we thought, which is maybe they're not even out there. The reason why we're only seeing Jupiters is because there's only Jupiters to be seen. No, that's not the case. In fact, small planets are very common. This plot only goes down to Earth-sized planets, but Kepler found things that were as small as like a hunk of rock the size of a city. That was in front of a very small star, a so-called white dwarf star at the end of its life. But it found all kinds of sizes of planets. Is there another question? Go ahead, Angela.
There is, from Elizabeth. What is the most common size of planets? So I know you said based on this diagram, it looks to be the green super Earth size.
Yeah.
But this is just one snapshot. So I guess that's a big question.
That's true. Elizabeth, I wonder if you think about, you sound like a very scientific person. So in order to go from this plot and reverse engineer the intrinsic occurrence of planets, you would have to take into account two things. You would have to take into account the number of planets you actually found. And then you would have to take into account the ability of your mission to see planets that are that size. So imagine that you only had a 10% chance. So you have designed your mission to be the best it possibly can be. However, you can't design it to be perfect. You've designed it so that around any given star, you have a 10% chance of seeing an Earth-like planet. Then let's say you see one of them. You would have to say to yourself, in order for me to have seen one, I know that I would have missed 90% because I understand my mission. That must mean intrinsically in nature there were 10. So you would have to reverse engineer very carefully from your observed sample of planets and your understanding of what you would have been able to detect what the true underlying rate of planets is. It does turn out that this figure does a pretty good job of conveying the intrinsic occurrence of exoplanets as a function of the radius, where we now know that super Earth-sized planets are actually the most common. My colleague Leslie Rogers, who's a professor at the University of Chicago, likes to say that these super Earth-sized planets are 80% of the planets in the Milky Way, but 0% of the planets in the solar system. And that's very strange to us. That's very strange. So we rely upon exoplanets to understand something which apparently is very common in nature, which are these planets in between Earth and Neptune. What are they like? Could they have a side? Go ahead,
So
Michelle.
we are getting so many questions.
That's cool.
On from this slide, I promise. So 2 more questions that we have is we have from Ishan and Krish, who are aged 9 and 4.
Yeah.
They would like to know, what is the distance the Kepler can see?
Yeah. Oh, okay. So first question, and now is that from Han or Chris?
That's from both of them. They must.
But from both of them. Okay, from both of them.
Yes.
Yeah. Okay. So the furthest planets that Kepler can see, it depends on how it was looking for them. The furthest planet that Kepler found was actually on the other side of the Milky Way. So you can imagine, like, if the Milky Way, it's more or less a disk like a pizza, and we're almost to the crust on one side of the pizza. It saw planets that were on the other side of the pizza, like halfway through that slice. So it saw things on the other side, like across through the middle to the other side, but it didn't see very many of them. Most of the ones that it saw, and imagine, so that's tens of thousands of light years, where a light year is a unit of distance. That's how far light takes to go 1 year. The moon, for example, is 1 light second. The sun is 8 light minutes. So most of the planets that Kepler found were between tens to hundreds of light years. So it's still roughly off of our back porch, like a slice of pepperoni away, give or take. But it did find things that were on the other side of the pizza sometimes.
Amazing.
Yeah.
I can't wait to find out more if we're able to. But this is amazing so far. And then before I let you move off this slide, which you may actually be answering later. So both Alex and Lily asked a similar question, and kind of, what are these exoplanets made of?
Yeah.
And
right.
are we able, we see their size, but are we able to actually know what they're made of too?
Yes. That is a field of study that dozens to hundreds of scientists are working on, is how to turn measurements that you get about planets into an understanding of their intrinsic properties. So what I've shown you here is the radii of planets, which is the physical size of the planets. That doesn't tell you how much the planets weigh. So in order to figure out, imagine the difference between like a heavy magnet, which you could hold in your hand, and that would have a particular weight. And then something like a sugar cube, or maybe a cotton ball, or like a foam piece, like those are the same size. They take up the same amount of space, but they have very different mass, and they're made of very different things. So in order to tell what planets are made of, you need often multiple pieces of observation to make that conclusion. Now here I've given you size. Then, as a result of hundreds and thousands of person hours to go to a telescope and use a separate method to determine how much the planets weigh, you can get a density. And that might be a word which is familiar to some people listening, the density, which tells you more or less what it's made of. So dirt, for example, about 5 grams per cubic centimeter. So pretty close to a sugar cube, roughly in density. Although we have found things which are much denser, like iron, for example, which is more like 10 grams per cubic centimeter. So that's how you figure out what the planets are made of, is you combine different pieces, different measurements, radius, mass, and then at the very end of this talk, I'll talk a little about how you can tell what the atmospheres are made of, where we have a separate trick for that. Okay, so thank you all for your wonderful questions. You're very thoughtful listeners. Okay, so this is what we've learned from Kepler. So let's go back to the slide before. I'm going to show you an updated version of this family portrait. Okay, it's going to have the same information, which is showing you roughly to scale the sizes of the stars around which Kepler found planets, and in front of them in shadow, the sizes of their planets. So this is an updated version of that from 2013. Now Kepler, we've continued, even though Kepler itself stopped working in this exact same way. About 5 or 6 years ago, they repurposed it. The folks at NASA repurposed it to study exoplanets a little bit more, and more planets are still coming out of that data. But this gives you a good sense for a good snapshot of what Kepler was able to find. Now, I want to point something out to you. And if you don't remember much from this talk, I would like you to remember this. So here's just a inset of some of these planets, okay? You can see how many stars there are. The color here is actually showing you the temperature, give or take, of the star, and this is roughly to scale their physical size. Now in this inset, Jupiter transiting the sun would be about that size. So going from the bottom where the stars are smallest, Jupiter transiting the sun would be about 2/3 of the way up this figure. So what that means is that the vast, vast majority of stars around which Kepler found a planet are smaller than the sun. Now that is very intriguing to me, and it should be very intriguing to you too, as a person who might be very Earth-centric in your understanding of where life would possibly evolve in the Milky Way. Like the primary so-called science driver for Kepler, the number one science it was supposed to address at launch, was what is the frequency of Earth-like planets transiting sun-like stars? And you can imagine we would want to ask that question because we want to understand ourselves. Human beings want to understand ourselves. But it turns out that the Milky Way and in nature doesn't actually make planets most commonly around sun-like stars. It seems to prefer to make planets around smaller stars. And in particular, it prefers most to make them around the smallest type of stars that nature makes, which are called M-dwarfs. These are things which are half the mass of the sun and smaller. And if you were a person who was interested in whether life exists elsewhere in the Milky Way, you would be so excited to hear that sentence. And why? It's because these small stars themselves are the most common type of star in the Milky Way. So, and yet, even though they are 80% of the stars in the Milky Way are small stars, so-called M-dwarfs, half the mass of the sun and smaller, 80% of the stars that are there, they are 0% of the stars you see with your eye when you look. You can't see a single one of these stars with your naked eye because human beings evolved to see light that comes from our sun. These small stars are much redder and much dimmer than light that we can see from our home sun, and yet they are 80% of the stars that are out there. What does that mean? It means that when you go out and look at the night sky, okay, you can see a certain number of stars. If you are able to see M-dwarfs, all of a sudden you would see 8 additional stars appear, give or take, for every star you can see with your naked eye. These are everywhere in our galaxy. And now, from what I've told you, something really exciting, which is that they host planets most commonly. So that is something which would make you feel really optimistic. If you were a person who is interested in finding life elsewhere in the Milky Way, you would say, not only are planets most common around M-dwarfs, M-dwarfs themselves are the most common type of star in the Milky Way. So that really sets us up for an understanding where planets, petri dishes in which life might potentially evolve, which are Earth-like planets around stars, are very common. In fact, there are hundreds of billions of them in the Milky Way alone. There are probably as many planets as there are stars, if not more. So that's something incredible, and I'm going to try to contextualize that now a little bit, because that's a lot of big numbers. It's hard even for a person who has studied astrophysics for her whole adult life to grasp something like that. The implications of that are really big, so I'm going to try to break it down to pieces where you feel you've really got a grasp of what that means. And I'm going to start with this figure, which is just showing our backyard. Okay, so this is a bit smaller than maybe a slice of pepperoni. This would be like a peppercorn or something. So, but this is showing the sun in the middle. And these are showing the stars that are off our back porch. Okay, so the radius of this sphere from which I'm drawing these stars to show you is about 10 parsecs. A parsec is about 3 light years. So this is going out about 30 light years. So the stars at the end of this sphere, at the rim of the sphere, would be able to receive a message from Earth 30 years after it was sent. You know, so they're just getting episodes of MASH or whatever it was on like 30 years ago, Twin Peaks. So they're like just hearing from us, okay? So that's 30 years already. So these are stars for which if you wanted to send a message in a human lifetime, you would be able to hear back. But this is just off of our back porch. The colors are showing you the type of star that they are. The red is showing you that they are an M-dwarf, half the mass of the sun and smaller. So now you can see in another way how common these are off our back porch. Even though you're with your naked eye, you're only seeing really the yellow stars. Okay, go ahead, Angela.
We just had a quick question about actually the colors associated with the stars. So
yes.
For age 12 was asking, are the blue stars hotter than the cream color or the yellow or, you know,
yes,
orange or red? Like, what do these colors mean for temperature?
Yes. The way that stars work is that the temperature does determine the color of the star. So the temperature here is telling you how hot the star is. Usually human beings associate red with hot and blue with cold, but stars aren't that way. The hotter the star is, the more blue its light is, and the cooler the star, the more red its light is. So that might be a little bit the opposite of what you would expect. But that's how stars are. And the sun, right in the middle, yellow. Yellow to greenish is the light that our own sun emits the most. So the blue is showing you the hottest of the stars that are in the sample, then yellow and orange a little bit cooler than that, red are coolest of all. And those are the small stars that are also the reddest. Stars are like a whole separate thing, which could be, a whole separate talk about how interesting they are as a family of objects and how they work. Okay, so here's a prediction. Now, this was made by a graduate student named Courtney Dressing. Time has passed, and Courtney Dressing is now a professor at UC Berkeley. At the time, she was a student, a graduate student in her mid-20s, and she was working on how common planets are around small stars. And she worked out from the Kepler mission. Okay, so Kepler wasn't necessarily looking at stars in our backyard. It was looking at stars in a particular patch of the sky. It wasn't looking everywhere around us to see where they are. What she worked out is from the yield of planets from Kepler around small stars, you have to make an assumption, which is that stars in that patch of the sky aren't special for any reason. The things we learn about stars in that part of the sky and how they host planets must certainly be true for other parts of the Milky Way, including the one that we live in ourselves. So she worked out, based on how common small planets are around M dwarfs in the Kepler field, how common they must be near to us. And she worked out with 95% confidence there's an Earth-sized planet in the habitable zone. So that means the right distance from the star where water would be in its liquid phase, as opposed to its ice phase if the planet were too far away, or its gas or steam phase if it were too close. So you're talking about an Earth-like planet with liquid water, right temperature for liquid water, within 18 light years. Now remember that the radius of the sphere is 30 light years. So what she worked out is it's probably one of these stars that has an Earth-sized planet in the habitable zone. Now this was before we went and actually looked for it. She worked out that it must be there. And she said, okay, and then taking into account the likelihood of transit, because you have to have a very particular geometry for the planet to pass in front of its star. From your point of view, planets and their stars are aligned every which way. So she also worked out, including geometry, you might have to go out a little further to actually detect it. And she was so right. She was so right. So indeed, based on what she understood from the Kepler field of view and how common planets must be around nearby stars, she inferred there must be a transiting Earth-sized planet in the habitable zone of its star within 18 light years, 100 if transiting. And there, this whole time, the whole time that humanity has been on planet Earth, there have been Earth-sized planets around the star TRAPPIST-1, which a few years later we discovered. This small star, very, very small star, this is an M dwarf, and almost at the smallest part where nature makes stars. Okay, so it almost isn't a star. It almost just doesn't have enough mass to be a star. Very, very tail end of what counts as a star. It has at least 7 planets, and 3 of them are in the star's habitable zone. And what you can see from this artist's illustration is how close to the star water would be steam and how far away water would be ice. And you can see that 3 of these planets might be the right temperature where you would have liquid water. Now, this was an amazing discovery. And TRAPPIST-1, I think, is still, or the TRAPPIST-1 planets are still, I think, the closest transiting planets. But in the meantime, we discovered that our closest star to the sun, which is Proxima Centauri, has itself an Earth-sized planet in its habitable zone. Okay, so that planet doesn't transit, and it was discovered in a different way. But what we now know is basically every single small star hosts a planetary system of some kind. And so I just wanted to show how that worked out, how a scientist statistically inferred from data that planets ought to be there, but you didn't know exactly where. And then time went on, and sure enough, we found it. So that was a really, really cool thing. There are probably planets with questions about M-dwarf stars right now. So I wanted to contextualize then what that means for like exactly how far away we're talking about. So I wanted to give this picture. Now, this isn't a real picture of the Milky Way because we can't take a real picture of the Milky Way because we're stuck in the middle of it. So this is a picture of the Andromeda Galaxy, which is a nearby galaxy to Earth, and it looks pretty similar to what we think the Milky Way looks like. So I'm going to scale this to the size of the United States. Okay, and let's say that we're here, okay, in this part of the United States. Now, you might be listening to this talk anywhere in the world, but put yourself in Miami, Florida, where the Frost Museum is, and now ask, then where is the nearest alien Earth-like planet? How far would I have to go in my galaxy? Okay, so if I've scaled it to the size of the United States, where are these strange worlds? And you might think maybe New York. You know, like it's hard to put human scales to big ideas like exoplanets and the Milky Way is so big. It turns out it would be so close to us. So let's say that Earth was at the Frost Science Museum. You would have to just walk 3 blocks to find the nearest Earth-sized planet in the habitable zone of its star. Okay, so if the whole Milky Way is the United States and you're at one side, you would have to walk 3 blocks. And that is really something to think about, considering that only 10 or 20 years ago, I mean, there might be people listening to this call, I'm sure, who were born after 1995. 1995 was when we found the first planet around another star, other than the sun. So the entire time you've been alive, we've known that there are planets around other stars, but that's not the case for me. You know, I was born in 1984. In my childhood, we didn't know of a single other planet around another star, and now we know they are. You can just reach out your hand practically and touch one. They are so close to us. I mean, astronomical scales are big scales. It's not really the end of your hand. But you understand what I'm saying. Metaphorically speaking, they're right off of our back porch. The nearest star, you know, that's like thinking that the next house over from you, no one's been living there, and then you find out your whole life there was like a whole family there. You know, that planets are incredibly common, and that probably makes you, if you're anything like me, think, I wonder if life is common. You know, and it would make me more optimistic because there are so many places where life potentially could evolve. Yeah, go ahead.
I'm glad you brought up about life because we've been getting a lot of questions about that.
I bet, yeah.
People are very curious to know, you know, has life been found on any other planets? Has, you know, you mentioned a little bit about the water and the one finding that was known, but, you know, how common is it that there would be liquid water on these?
Right.
And, you know, would that mean the chance for aliens? And how do we even start searching for that? And we're just getting all these questions.
Yes. Yeah. I'm gonna address that as much as I can in the time that we have, because I wish I could give you the answer. We are like right in the middle of the time that we're answering that question. So 5 or 10 years ago, the question was, are there even other planets? Now the scientific community among astronomers is really gearing up to ask, is there life around these planets? We have not discovered life on another one of these planets yet. But just like with exoplanets before, when we could only find hot Jupiters, it wasn't because other planets weren't there. It was because we didn't yet have the tools to see them. They were there just waiting to be found. Now, I don't know that will be true for life, but we're in a really similar state right now, which is we just have to have the right tools, and those tools are being built right now. And if there are questions in particular about what they are, there's a series of missions in space. It's much easier now. To find a planet is already hard enough. To be able to study its atmosphere for signs that the atmosphere is inhabited is much harder. You know, roughly a factor of like a million times harder, like give or take, in terms of just like the size of the signal. It's doable, but you often need a platform in space so that you don't necessarily have to look through the atmosphere, which is very hard to do, to observe outer space. It adds additional steps, which can be hard to deal with. And so you have to go to space, and you have to have an extremely big eye, bigger than the eye of Kepler. You know, it has to be like half the size of a football field, give or take. And that those telescopes are coming online, the James Webb Space Telescope and so on. And you have to be able to find the planets that you want to look at. You can bet that the TRAPPIST planets are really high on the list of the first things that we're going to look for. So I want to start talking about life. And it's really interesting to be giving this talk to a public audience right now. And because to have a conversation about life evolving elsewhere isn't just a question about life around sun-like stars. Okay, so just in terms of the statistics of what we're talking about, we ought to be thinking about life around small stars because those are the most common type of star and they most commonly coast small planets. The nearest habitable planet to Earth is around a small star, you know, and they really have the advantage of numbers. So it would be short-sighted of us as a species, even though we live around a sun-like star, to limit ourselves to thinking about life on sun-like stars. The numbers point to the likeliest nearby life being around a small star just by virtue of them hosting the most planets. So this is one of the more complicated figures that I'm showing in this talk, but I'm sure there will be people who will grasp it right away. So this is showing as a function of distance, the x-axis, horizontal axis is showing you as a function of the distance of the planet from its host star. On the y-axis is showing you how massive the star is. The orange swath is showing you where the temperature is right to have liquid water. Okay, so for a small star, those are they're less luminous. You have to huddle much closer to that campfire to be warm enough. As the star gets more and more massive, okay, so you're going up the vertical axis, the place where you would be warm enough for liquid water, you have to move further back. Okay, so the orange swath is the habitable zone. There you see the solar system. Okay, so you are here in the middle of that orange swath for a G-type star, which is a sun-like star. For M dwarfs, which are smaller, look at how you have to be much closer to the habitable zone. Crucially, you're inside of that dotted line. What does that mean? It means that you're talking about really different physics that comes into play if you're around a small star. You have to huddle much, much closer to the star, which means you're even inside something called the tidal lock radius. Now, the moon, for example, is inside of Earth's tidal lock radius. That's why the same side of the moon is always facing the same side of the Earth. We never see the far side of the moon from Earth's surface. So that we think would happen. Okay, so in terms of the physics that we know and understand, which applies to everything else that we've seen, it probably follows that planets that are around these small stars in their habitable zone don't have a day and night. Okay, so what that means is the same side of the planet is always facing the same side of the star. And that's so hard to, oh, sorry, I just haven't updated this since I gave a talk at MIT. That's so hard to understand that I like to actually turn to fiction or poetry or other ways that human beings try to understand really big ideas to try to internalize for myself as a human being what that would mean. And I'm going to read from you just really quickly an excerpt from a novel that's called Einstein's Dreams. This is written by Alan Lightman, who is an astrophysicist, and then he went on to write a lot of really wonderful fiction. Einstein's Dreams is a book where it's an imagined journal of Einstein. So he imagines that it's Einstein's journal entries, and he is imagining to himself, what if time operated differently? What would the human experience be like? And in particular, on an entry from the 3rd of June, 1905, he imagines a world that would be like this. Okay, so more or less permanent day and permanent night. Imagine a world in which people live just one day. Either the rate of heartbeats and breathing is speeded up so that an entire lifetime is compressed to the space of one turn of the Earth on its axis, or the rotation of the Earth is slowed to such a low gear that one complete revolution occupies an entire human lifetime. Either interpretation is valid. In either case, a man or woman sees one sunrise and one sunset. In this world, no one lives to witness the change of the seasons. A person born in December never sees the hyacinth, the lily, the aster, the cyclamen, the edelweiss, never sees the leaves of the maple turn red and gold, never hears the crickets or the warblers. A person born in December lives his life cold. Likewise, a person born in July never feels a snowflake on her cheek, never sees the crystal in a frozen lake, never hears the squeak of boots on fresh snow. A person born in July lives her life warm. The variety of seasons is learned about in books. And I think that's a really good way through art to imagine what life would be like if you were a creature that lived on this planet. So permanent day, permanent night means you would never know. If you were born on the night side, you would never have seen the sun. If you were born on the day side, you would never have experienced night And you can imagine if you were in a classroom, a creature in a classroom on that planet, you would learn about strange planets around larger stars that might have day and night. That would feel as strange to you as it might feel to us to imagine life on planets where there is no day and night. And it's unclear to me, give or take all else being equal, whether life prefers one or the other to evolve. That's a really open question. And that's only one way in which life around these small stars would be very different than life around the sun. For example, if for folks who are astronomy enthusiasts, if you've ever heard about Jupiter's moon Io or seen pictures of it, Io is the closest moon to Jupiter. And Jupiter is roughly, give or take, the size of one of these small stars. And Jupiter's moons are close enough to where that would roughly be, if Jupiter were a star, the habitable zone for the moons of Jupiter. Okay, so to scale, Jupiter and its moons is not that far from an M dwarf and its planets. And Io is so close to Jupiter that if you've ever seen a picture of it, it looks like a pizza. Like it has, it's constantly being repaid by volcanic activity because it's so close to the star that not only are tidal effects happening to make the same side of Io face the same side of Jupiter, it's also that tidal forces are stretching and squeezing Io so that it has a constant magma core composition in its core rather than getting to cool and being solidified. So you can imagine that doesn't sound very habitable to me. Okay, so that sounds like that sounds dangerous even. You know, how could life evolve if you have constant volcanoes going off? But on the other hand, there might be a way. We think plate tectonics are so important to the long-term climate stability of Earth. And our plate tectonics are due to, so we float on a magma core too. Our magma core isn't from getting tidally heated from our star, it's from radiogenic heating of elements in the core of our planet. But you can imagine, let's say you didn't have that. You might still be able to have plate tectonics if you had a little bit of tidal excitation. So there's arguments among astronomers, which is, okay, but maybe this is actually in favor of life, to be close enough to a star where you could have some tidal heating to make a magma core, because then you could get plate tectonics, even if you don't get it the Earth route. And there's other arguments, like a professor, Elmo Shields at the University of California at Irvine, has made an argument, which is that you wouldn't have ice ages on planets around these small stars. Well, why should that be? Because ice ages, that is something that has happened on Earth and really been catastrophic in important ways for life, or I should say it's shaped the story of life on Earth in really important ways. And it can be really hard to escape an ice state, because once you're covered in frost, you're even more reflective to light, so it's very hard to warm up again. Because snow is so reflective, as you know from seeing the snow, it's so reflective that it's very hard once you're a snowball to cool off. But that's not true for small stars, because snow and frost isn't more reflective for the light that small stars have. So it would be that redder and even infrared light. Snow isn't reflective at those wavelengths. So we might be protected around these small stars. Life might be protected. And then there's the thing that every person, if you're an astronomer, brings up immediately when we're talking about life on M dwarfs, which is, what about stellar activity? M dwarfs are really riotous their whole lives. Basically, like, the sun had a period of time really early on in its life where it spat out a lot of solar flares. It was incredibly active, lots of ultraviolet radiation, which could be very dangerous to life. And then it calmed down and came to its kind of like adult life, where it's currently sitting and will be sitting for another 5 billion years. That's not the case for small stars. They can be active their entire lives, and they live a very long time, much longer than the sun will ever live. So people have argued, well, what about a single stellar flare? That could kill life immediately, like a single UV photon, ultraviolet photon particle of light, can break a DNA apart. So people have argued, and we're protected from that by the oxygen in our atmosphere. We're protected from that by the ozone layer, if you've heard of that. But the issue of being on an M dwarf is, well, what if you're constantly bombarded with that radiation? How would you ever evolve structures like DNA? Wouldn't it break apart? And there's a lot of arguments about that, which is, well, maybe it would break them apart, but on the other hand, there seem to be really important processes in biology where you need a little bit of ultraviolet light to make basic proteins. So I'm trying to give you a flavor for what the conversation is like at a conference today in exoplanets talking about M dwarfs. Lots of talks would be about these exact topics. How exactly would this work? How exactly would this impact the evolution of life? If life evolved, what might it be like? Is it possible there would be long-term climate stability from plate tectonics, or would we have to say goodbye to that? And what about stellar activity? So I wanted to conclude by talking about how that would work, the remote detection of life. And it relies critically on an understanding of the molecular fingerprint of every molecule and atom that we understand. So, but what do I mean by molecular fingerprint? I mean that if you shine some light, and let's say white light, okay, so there's an equal number of red light, orange light, yellow light, all the way to purple light. You're shining that on a leaf. There is a very particular way that leaves interact with light. Okay, so you only get the green light back. That's why leaves look green to you. The leaf itself absorbs all the other light. So that means that even if you couldn't see the leaves on another planet far away, if you were somehow able to get it backlit, to be able to look at the light budget for what happens when light interacts with things on the surface of that planet or in its atmosphere, you could remotely infer from how life interacts with it, there must be leaves there, there must be plant life. And the same is true for other things which we consider to be really important to the evolution of life. Now, things like carbon dioxide, ozone, oxygen, and methane, these are things which we associate with life on Earth, but life is not the only way by which you can generate those things. So look at methane, for example. Volcanoes outgas methane. So if you looked at another planet and you saw the signs of methane, which you understand very well from looking at methane gas here on Earth, you would say, there's a particular way that methane interacts with light. I would recognize it here. I'd recognize it anywhere. And looking at another planet, you would say there's methane there. There still is another leap of logic where you would say, is it possible the methane is from a volcano? So that there will be much of an argument around that. This is the stage where we're at right now, which is trying to use tax-funded spacecraft like the James Webb Space Telescope to look at these planets. When they are transiting, they will be backlit by the star, and you actually have a flashlight backlighting the planet. You can look and see how that light gets filtered through the atmosphere and through a prism and look at what must be in that atmosphere. And that's some of the most cutting-edge science that there is right now in exoplanets. We've already done that, I should say, for a number of planets. Like we found sodium was the very first atom that we found in an exoplanet atmosphere, and that was 20 years ago, give or take, that we were actually able to see that, but that was a Jupiter. It gets much, much harder for small planets. So this is what I expect to see, for example, on like the front page of what's the biggest newspaper in Miami? The Herald? So like the front page of the New York Times or something would be in 5 years, I'm guessing. The detection of methane on an Earth-sized planet in the habitable zone of its star. And then there will be an argument, scientists will argue, and people will struggle to understand, is it possible that that means life? For sure. And I hope that gives you a little sense for where we're at. I was going to conclude just with this. This is not an image of an exoplanet. This is an image of Titan, which is the moon of Saturn, but it illustrates the exact principle I'm talking about, which is if you backlight the planet and you see how the light filters through the planet's atmosphere, you can unlock the mysteries of that planet to see whether it might host life. That's an open question, but what isn't an open question is whether the planets are out there. There are so many of them. And I guess at this point I'll stop and I'll take your questions.
Thank you so much, Sarah. This has been really, really fascinating. I'm
happy.
I'm so intrigued. I think I have more questions now than when before we started this conversation, to be honest. But we do have some questions from our guests. So
I'd love to hear them.
We have Sailor, who's age 8, that were asking, how many stars are there in the universe?
In the universe?
It's a tough question.
Yeah, I'm forgetting. So there's the number of, I think it's 100. No, there's 100 trillion galaxies, I think. Trillion is a 1 with 15 zeros after it. I think that's the number of galaxies, but then every galaxy has a 1 with like 9 or 10 zeros, numbers of stars in it. So okay, so offhand, I'm thinking like a 1 with like 25 zeros. I'm guessing. I could be wrong. There might be other astronomers watching this, and I'll be like embarrassed about that. But it's between like 15 and 25 zeros. That's my that's my range. A one with between 15 and 25 zeros after it. That's the number of stars in the universe.
That's a crazy large amount.
It is, yeah, I know.
And if we're saying that most of the stars end up actually having multiple planets around them too, I mean, that's just,
I know.
like, I can't even fathom the number of stars that means, and planets that means for a whole universe for us to look. So we're really just at the starting point and the cusp of this for science, and
we are
understanding this, which is very exciting.
Yeah.
We had a question from Jenna as well as, how are these discoveries of new planets beneficial to science, and how can this information be used?
Yeah, that's a really thoughtful question. There's the question of how it's beneficial to science, and then I think the question for how it's beneficial to people generally. And there's a lot of ongoing conversations about the role that science serves. Generally, like maybe there's the question about the role that exoplanets serves within science. And then there's the question about the role that exoplanets might serve broadly. You know, even within the community of people who don't consider themselves scientists, but might be interested in planets or just interested in life, interested in the mysteries of Earth. And one thing that I like to contextualize is I feel like understanding exoplanets for me feels very similar to maybe understanding microbial life, or I should say like the whole universe of things that are happening on a tiny scale, like even on your desk or on your hand, like or inside your body, because you can't see it, but it affects your daily life. And to be able to understand it helps you understand your human experience. And I think the same thing is true for understanding the universe generally, particularly for understanding exoplanets, because it's easier there. You can see the path toward understanding exoplanets is to understand how common life might be. And that helps us understand ourselves. Like, how did we come to be? And generally speaking, are we alone? I think that's one of the questions where either way, if the answer is yes or no, I think those are both incredible answers. And so exoplanets as a science informs so many other types of science. It informs like biology, chemistry, planetary science, our understanding of physics. Like, for example, it won the Nobel Prize last year. Exoplanets did. So that's a sign of how the scientific community values them. But also, whether or not there's life is something which I think is interesting philosophically, too. But I know that there's a long ongoing story about what we ought to fund with precious taxpayer dollars, you know, and I understand that that's something not just one scientist can answer. I have a vote. I think exoplanets are cool, you know, but there's so many other things that are cool too. But a great question.
Absolutely. And, you know, I think it's really important to note that, you know, this is one problem of many that we're trying to look at and solve all simultaneously, and really gain. So the final question is one for me, which is just, where do you see this field going, and what are kind of some of the discoveries you're hoping to see, hopefully within my lifetime, but you just in the next 5-10 years, because as you mentioned with Kepler, once that happened, it was so quick.
I can tell you how I think things are going to look for me. So here I am, one scientist who really had her career launched by transiting exoplanets, right? So I rode the wave. It didn't have to be the case that nature would make planets so commonly, and that transits would be a method where all of a sudden, because of the Kepler mission, transits were a really hot topic, and we had discovered thousands of planets. I think that's going to go away. Generally speaking, because to understand planet atmospheres and to understand the prevalence of life is really where the field is going generally. You can do that with transits, with this backlight method. What you'd really like to do is just take a picture of the planet. You would love to do that. You would love to have Carl Sagan's pale blue dot image of like an actual planet, light from that planet in a pixel, separate from the light from the star in another pixel. Now, that is an extremely hard technical achievement to be able to do that. Extremely, extremely hard. But we are building the tools to be able to get there. I think we're like 10 years away, like the really large telescopes, the 30-meter telescope types, like the Great Magellan Telescope and so on, Giant Magellan Telescope. So that's the direction the field is going, is I want a picture. I want to be able to directly image, because once you have a picture, you could also if the planet is rotating, you can see how the color of that dot might change with time and make a guess about whether it has continents or oceans. You could maybe even see a glint of the ocean, you know. Like those are levels of things where you could understand these planets in a detail that we can't today. So I think that's the direction the field is going. Frankly, I think between 10 and 15 years from now, most of the debate is going to be, does this signal mean that there's life there? And there will be arguments about that. So it'll be, and making a guess in conferences, on the front page of newspapers, it'll be like, this is a discovery in which there is both methane and ozone in a planet, and scientists arguing, does that mean that there must be life there, or whether it's possible there's some other way for nature to make those things, and it's not necessarily life until, but probably outside of our lifetimes, there's a chance to actually go, you know, to those planets and like just pick up a bug or something and like actually see, is there life? It's going to be a lot of arguing from far away, but maybe not for the children listening to this call, you know. But for you and I, probably it's going to be like that. I'm guessing.
Thank you so much again for taking the time out of your day to join us. This has been truly fascinating.
So welcome.
Be talking to you about a lot of questions after this.
Okay.
But thank you all to our wonderful listeners for joining in as well. We hope you enjoyed it. We have our next virtual live at Frost Science. It's next Wednesday at 2 p.m. and it's going to be with Jillian Morris, who's the founder of Sharks for Kids. So it's all about sharks. So be sure to check that out. And we hope you have a truly wonderful rest of your day.